Hello, this is Professor Keen, and I've been lecturing on Newton's Principia, Book 1. We are now in Section 2, and we're specifically talking about Newton's Proposition 1, Theorem 1. And that's what I have shown on the screen here. Remember, Proposition 1, Theorem 1 claims that the areas which revolving bodies describe by radii drawn to an immovable center of force, first of all, they lie in the same immovable planes, and second of all, they are proportional to the times in which they are described. In my previous lecture, I explained point 1. So remember the situation here was that in this diagram, I depict a center of force. Let me get my colored markers up here. This point right here, S, is the center of force. We had imagined an object that started out at point A. It was moving along this line at a constant or uniform speed. It's going along from A to B. So at a later time, it's at point B. And the idea is we are dividing, we're breaking this up into small time increments. So in a time delta t, it moves from A to B. The distance AB is the distance it moves in that time. If there was no force acting on it, it would have ended up at point C. But we're imagining at this particular moment in time, at point B, there is a force that is acting on it, directed in the inward direction. That is the centripetal force that's acting on it at that moment. And that deflects the trajectory, so it ends up at this point right here. So let me actually use some different colors here. So this would be the trajectory that it moves during the first time interval. And then during the second time interval, it moves along this trajectory, and it ends up at point C. And the point that we made last time was that if this force lies in the same plane as line AB, and more specifically in the same plane as this triangle ABS, then there is no change in momentum or change in motion out of this plane. And so this new triangle SBC lies in the same plane as triangle ABS. And so that's this first point that he's making right here. So I'll underline that. They lie in the same immovable plane. Okay? Now, secondly, and this is what I'm going to focus on right now, is that these areas, the area, for instance, SAB and SBC, they are proportional to the times in which they are described. That's what I want to talk about right now. Okay? So let's go through Newton's explanation of this. So let's look at triangle. Let's look at triangle SAB and triangle SB little c. So we're going to be looking at these two triangles, and why don't I let me color code them. So triangle SAB, that is this one right here, SAB. So we're going to focus on this triangle, and also let's do this one in yellow, triangle SB little c. So that is going to be this one right here. Okay, so let's focus on these two triangles. Just a little bit darker so we can see it. Okay, now I'm going to claim that these have equal areas. They have equal areas. That is, triangle SAB is equal to triangle SB little c. Okay, how do we know? So how do we know that that's true? Well, remember that the area of a triangle triangle, you might remember this from your geometry class, the area is equal to 1/2 the base times the height, right? That's the area of any triangle. So let's look at what the areas of these two triangles are. Well, it's not obvious that they have the same base and height until maybe what we can do is we can look at it this way. Think about triangle SAB. This right here is the base of triangle SAB. And think about this right here as the area, that's the base of triangle SB(c), right? So if this ball or this object was traveling in a straight line from A to B in some time interval, and if there was no force kicking it at point B, it would have gone during the same time interval, the exact same distance, BC, right? So that's the principle of inertia. So they would have gone the exact same distances. So these two bases of these triangles are in fact equal. Now, what about their heights? Well, how do we think about the height? Remember the height of a triangle. If I extend this line right here, the height of a triangle is if you take the apex or the vertex of this triangle and drop a perpendicular line down to the extended base, that is the height of either one of these triangles. So this is the height, technically speaking, that's the height of both triangles. So if you're not quite clear about that, if I draw a triangle like this, this would be the base of the triangle. And if I extend that line right here, that is the height of the triangle. And so we're kind of turning these triangles sideways. Since they both have the same base, and since they both have the same height, that means that they both have the same area. Okay, so that checks out. So those two triangles have the exact same area. But of course, this object, it felt a force right here, so it doesn't end up at point C. Instead, it ends up over here at point big C. So now what I want you to do is I want you to look at triangles. First of all, triangle SBc and triangle, and let's make this one a blue one. Okay, let's look at this triangle right here. Since I've already drawn it blue partially, right here. So that one. So triangle SB big C. Okay, that's big C. And the claim is that these have equal areas as well. In other words, triangle SB big C is equal to triangle SB little c. That's the claim that I'm going to make. Now, how do we know this? Well, once again, the area of each is its base times its height. Now let's take the base to be the line SB in both cases. So both have base SB, right? And what is the height? Well, the height of both triangles is going to be the distance from the base to, they both have, this one ends over here, it's little c, this one ends at big C, but notice that this line right here, CC, is parallel to the line BS, or SB, because that force that we applied at point B directed toward S caused its momentum to change, and the change in momentum is in the same direction as that force. That means that whereas it would have ended up here at little c, the change momentum is in the same direction that is parallel to that force which is directed along BS. So this line here, the change in momentum, the change in direction, is parallel to that. So this line right here must be parallel to SB. That means the distance from the base to the vertices of both of these triangles is the same. So they have the same height. So end the same height. Therefore, they are equal in size. So we've just demonstrated that if you have an object that's moving at a initially constant speed and you apply a force directed toward a point S, it's deflected, and the area that is constructed inside of point SAB, that area right there, is equal to the area of the yellow triangle, and it's also equal to the area of the blue triangle. In other words, since we've shown that the green and the yellow triangles have equal areas, and we've shown that the blue and the yellow triangles have equal areas, then by transitive property, you might say that the triangle SAB has the same area as triangle SB big C. So these two triangles have an equal area. So when we apply this force, it changes the trajectory of the ball, but the area that is swept out between point S and the trajectory of the ball, that area of that triangle, is the same as it was in an earlier time interval. Okay? In other words, a sudden centripetal force directed toward S, toward point S, causes equal areas to be swept out in equal time intervals. That's the point that is being made right here. And by swept out, I mean, he says if you draw a radius from the center of force to the location of the ball, and you imagine that radius sweeping out an area, the area during the first time interval, and then you apply the centripetal force, is going to be equal to the area swept out during the second time interval. So we've shown that the sudden application of a centripetal force on a body that's traveling in an initially straight line past this point S causes its trajectory to change, that the area swept out lies in the same plane as before. That's what I showed during last lecture. And also that the body sweeps out equal areas during equal times. Okay? Now, I've shown that if you apply a force at point B, but if you repeat this process, so the ball is traveling along this line BC, it would end up at little d, but if you apply another centripetal force inward at this moment, so apply another force, once again, the trajectory changes. So whereas it would have ended up here at point D, now it ends up at point big D. And we could, using the exact same arguments as before, say that this triangle SBC, the triangle SBC, is going to have the same area as, let's make this a red one, as this triangle SCD, using the same arguments as before, SCD. Those two triangles are equal. And likewise, if it was going to go up, if it would have ended up here at point E, but we apply a sudden centripetal force at point D that's directed inward again toward point S, it deflects once again, then it would go over here to point E. Okay, so then the object would go like this, and then apply another centripetal force, and it would go over like this. And each of the areas swept out would be the same. So if it sweeps out the same area during the first time interval, the second time interval, the third time interval, the fourth time interval, the fifth time interval, each of those intervals, it sweeps out the exact same area, then Newton claims that the area swept out is proportional to the time it's described. So if you consider just the first time interval, if it sweeps out a certain area, during the first 3 time intervals, it's going to sweep out 3 times that area. During the first 4 time intervals, it's going to sweep out 4 times the area. Okay? That's the argument that he's making here. Let me get rid of these. I want to make a couple of more points before I go on. Okay? Notice that we made no assumption. We made no assumption about the size of the time intervals. The size of the time intervals between the application of centripetal forces. Centripetal forces, delta t. So we said we're going to wait a time delta t, apply a force, wait another time delta t, apply a force, wait another time delta t, apply a force. But we could take these delta t's to be smaller and smaller and smaller, right? So if we had, in our previous diagram, we had it's going up here, we apply a force, then it goes to there, we apply a force, then it goes to there, we apply a force, then it goes to there, we apply a force, then it goes to there, we apply a force, right? So we have all of these forces applied at each of these moments in time, right? So it's going in this direction, then this direction, then this direction, then this direction, then this direction. If you take a limit as delta t approaches 0, so take kind of a limit in that case, what's going to happen, so again, this is point S, you're going to have this go over to vary time intervals, and it's going to go over to a smooth curve. So you have many, many, many of these forces being applied closer and closer and closer together, and you're going to have this moving along a smooth trajectory in the limit as delta t goes to 0. Okay? So if you think about a given time interval, a radius drawn to the point where that object is, during that time interval it's going to sweep out some area, but if you consider 4 times the time interval, 4 times as big, it's going to sweep out 4 times the area, because every single small time interval it sweeps out the same area. That is the area swept out is proportional to the time elapsed. What is the point of all this? What Newton is basically doing here is he's arguing that if an object feels a centripetal force as it's flying past a center of force, it feels a centripetal force toward the center, that the area that it sweeps out will be proportional to time. And eventually what he's going to do is he's going to reverse this and say, if you see an object that is sweeping out areas that are proportional to time, then it must be feeling a centripetal force. This is going to be a very important key aspect of his argument about planetary motion. So why don't I stop there?